Hey guys, welcome to this video. In this video, I want to discuss an interesting question, which is what's the relation between symmetry and temperature, if any? First of all, let's start with a very interesting question. Which is more symmetric, solid or gas? Solid means I'm talking about a crystalline solid. It's not an amorphous solid or anything. It's a perfect crystalline solid. It's a crystal lattice. If you know what a crystal lattice is, it's like the same periodic arrangement in all three dimensions, like a lattice, 3D lattice. There is a fundamental cube, and that is repeated in all three directions. And all the edges of the cubes, they are the lattice sides, or that is where the atoms of the solid occupy, and the remaining are the free space. And the edges of the cube, the line connecting two vertices or two atoms, we model them as springs, because this is just a model. Of course, actually in a solid, atoms are not connected by springs, but we model them by one-dimensional springs because these atoms vibrate, and to model the vibration we use the concept of simple harmonic oscillation, like one-dimensional springs. So that's a crystalline lattice. And as gas, we all know what a gas is. A gas is just a random collection of gas molecules which are just in free space, no external force or anything. They're just floating around, roaming around and everything. So which is more symmetric? So what is symmetry is a very interesting concept, which a lot of it's usually generally misunderstood at the undergraduate level, or even at higher levels, because symmetry is something important. It's not like what we do in high school, for instance, a square is symmetric because if I just, of course that is symmetry, but that is not the best way to understand symmetry, at least the symmetry that is important in theoretical physics. Okay, so if I say square is symmetric, if I say anything is symmetric, what I actually mean by that is under a certain type of transformation, some aspect of the system does not change. This is the number one point, the main thing of symmetry. At that aspect which does not change, we say that is the conserved quantity in terms of physics. Like for instance, let's say we have an equilateral triangle. So if we have an equilateral triangle, and if I just kind of drop a perpendicular bisector from one of the vertices to the opposite side, since it's an equilateral triangle, it will bisect the opposite side, right? And now if I just flip the triangle along that line, that axis of symmetry, then of course I will get back the same triangle. I'll get back the same triangle in the sense the orientation of the triangle will not change. Now if I take a solid triangle and if I mark one side A and the back side B, and if I do this transformation, then of course I can differentiate. Okay, this is A, but now after a flip I can see B, so they're the opposite sides. But if I flip twice, then I will again get back A. So if I can distinguish both sides, A and B, then I have to rotate it twice. I have to flip it twice to get back the same orientation. So flipping it twice, this is the transformation under which the orientation of the triangle does not change. And if I cannot distinguish A and B, like if both sides are the same, then even a single flip will keep the orientation unchanged. So in technical terms, we say that the orientation of the equilateral triangle does not change under this flipping transformation. Flip is basically a transformation, and that is what we mean by symmetry. The equilateral triangle is symmetric under this transformation. Its orientation is symmetric, rather, I should say. Right, so very important point, okay. Now, see, there are many possible transformations under which the orientation will not change. For instance, if I rotate the equilateral triangle by 120 degree, this way, you can understand, right? If I just rotate it along one of its sides, then also the orientation will not change. You will not be able to distinguish. If you mark the sides as A, B and C, then of course you will be able to distinguish, but otherwise you will not be able to distinguish. The orientation will still remain the same. So all the possible transformations which leaves something unchanged, they form a symmetric group for that quantity, for that thing which remains unchanged. In our case, orientation, let's say. So this is the basic idea of symmetry, okay. Now in mathematics, of course, when we're trying to do mathematics, physics, we need to have some quantitative representation of symmetry. What I said so far is just a qualitative discussion. So any kind of linear transformation, see, if it's a non-linear transformation, it's something else. But if it's a linear transformation means, for instance, rotation, even this flipping, or even translation. Suppose you have a point here, you just want to shift it here, just move it horizontally some units to the right. All these transformations can be represented by matrices. Suppose if you're doing a transformation on a two-dimensional plane, say XY Cartesian coordinate system, you need a 2x2 matrix. Suppose the matrix 1, 1, 0, 1, it's, as far as if I remember right, it's a translation matrix. If you have a point on the 2D plane, say 2, 3, So you can represent it as a column vector 2, 3. Like 2 is the first element, the bottom element is 3. It's a column matrix. Right, it's 1 cross 2 matrix. I mean, it's 2 cross 1 matrix, 2 rows and a single column. And you multiply this, pre-multiply this with a 2 by 2 matrix. Suppose if you use the matrix 1, 1, 0, 1, you do the matrix multiplication and you again get a column matrix, 2 cross 1 column matrix. And this will be suppose A comma B, A, B. So if you plot the point A comma B, you will see that it has shifted 1 unit to the right. Because I took the matrix 1, 1, 0, 1. The second element 1, that is by that amount, the original point will be translated. If I take 1, 2, 0, 1, it will be shifted 2 units to the right. If I take 1, minus 3, 0, 1, it will be shifted 3 units to the left because I've taken minus 3. But anyway, all that is not important for the purpose of this video. The point is, you can represent a transformation using a matrix. There is a rotation matrix and so on. Depending on your dimension, like whether you're working on a 2D plane or a 3D coordinate system, you can take a 3 by 3 matrix as well. In particle physics, I mean in standard model, we use all these symmetry groups, SU3 symmetry group. That is, SU3 is used to model the strong nuclear interaction, SU2 for the weak nuclear interaction, then U1 for the electromagnetic interaction, if I remember correctly. But the point is that, what is U1? U means unitary. That means it has to be a unitary matrix. There are some properties of matrices. Okay, you can understand. There are these are just some mathematical properties. I'm not discussing them here. SU means special unitary. That means it has to be a unitary matrix, and special means the determinant has to be 1. So SU2, that means a special unitary matrix of order 2. That is a 2 cross 2 special unitary matrix. These transformations are usually they are square matrix, not any column or row matrix or any rectangular matrix. They are always square matrix. So SU2 means 2 cross 2 matrix. SU3 means 3 cross 2 matrix, which is unitary with a determinant of 1, special unitary. There is the SO matrix, special orthogonal matrix, or many more things. So that is what I mean by symmetry. Now, another way to look at symmetry is that you cannot distinguish between something, like I already said, something remains unchanged. So in case of a gas, gas is usually, gas molecules are free to move about. There is very little constraint. They are just free to move about. They are free to occupy all the space that is available to them, and over time, they will be colliding randomly. They will be distributing the energy uniformly through the entire system, and they will be since the gas molecules will be jiggling about like a random Brownian motion, you have a probability of finding a gas molecule at every point in space and time over if we have a lot of molecules which are freely jiggling about, right? So in that sense, a gas is actually more symmetric than solid. Why? Even than a crystalline solid. Why? Because gas has continuous translational symmetry. What do I mean by that? Let's assume you have an infinite gas, like the gas is stretching infinitely in all directions, like the entire universe, infinite amount of space it's covered by gas, suppose. So you are at point A and you look around, look everywhere around you, you see the uniform density of gas molecules, because over time the gas molecules will be moving about and the energy will be distributed uniformly, and you can find the probability of finding a gas molecule, like if you focus on a region, on a small region, the number of gas molecules in that region will be constant. That means uniform density. Of course, some molecules will be exiting that region, some molecules will be entering. But since it's random motion, if you fix a particular region, the number of gas molecules in that region over time will be constant. So everywhere you look around, you are at point A, you will see uniformly distributed gas molecules. Now suppose you shift to point B. Now since the gas is infinitely, it's stretching infinitely in all directions, so no matter if you shift a finite amount of distance from point A to point B, you will still see the uniformly distributed gas molecule everywhere. So in that case, how will you distinguish between point A and point B? You translate it from point A to point B, but nothing changed. Like you cannot distinguish anything. It's the same gas everywhere. So that means it's a continuous translational symmetry. Why continuous? Because you can move any distance. There is no restriction. You can move 1 meter, you can move 1.1 meter, you can move 1.01 meter, you can move 1 kilometer. You can move 1 light year, since the gas molecules are distributed infinitely in all directions. Solid. Now, although it's a crystalline solid, but crystalline solid means what? There are many cubes, and all those cube points, the edges of the cube, these edges. So suppose you are sitting at one edge of the cube, that is, you are sitting at one atom, one gas, one solid atom. If you are sitting on the edge or on one solid atom, then everywhere around you it's the same thing, because the cube, the solid lattice is also extending infinitely in all directions. To make a fair comparison, we will also assume that the lattice, the crystalline structure, it extends infinitely in all directions. So if you're sitting on an atom, everywhere around you can see the same structure repeating, so it's symmetric, you cannot distinguish. If you translate to the next atom, that means the length of the cube, the edge of the cube, if you translate by that amount, again you cannot distinguish because everywhere is the same thing. But if you translate by some lesser amount, then you will end up at a point which is between the two atoms, some point in between, which is not a solid atom but just some point in between, somewhere on the line joining the two atoms. In that case, suppose this is one atom, this is the another atom, and you are somewhere in here. So you are closer to the left atom, closer to this atom, and you are farther from this atom. From that point, you actually will be able to distinguish, okay, the left atom is nearer to me, this is farther to me. So you can distinguish left and right. That means the symmetry has broken. In solid, there is a symmetry, and that is called discrete translational symmetry. Discrete, why? Because you are allowed to translate, you are allowed to shift, but only by integer multiples of the length of the cube. If you do that, then the symmetry will not be broken, you cannot distinguish. But if you shift by any other amount, any other random amount, the symmetry is getting broken. That means it is no longer a continuous translational symmetry, it's a discrete translational symmetry. That's why actually a solid is less symmetric, I mean a gas is more symmetric than solid. Okay, now the analogy I want to draw is that which has higher temperature, I mean which exists at higher temperature, gas or solid? Of course gas, because water vapor, if you heat a solid, ice is a solid, and ice exists at comparatively cold, like lower temperatures. If you heat the ice, you get water, which is again like even water is, I guess you can think about it like this, water is more symmetric than ice, because again it's a liquid, so you cannot really distinguish in that sense. If you're in an infinite ocean with more or less uniform water everywhere, you cannot distinguish, right? If you heat it further, you get gas, which is very symmetric, right? Water vapor, so ice, water, water vapor. So think of it in the opposite way. When the temperature is maximum, then the energy is also maximum. Gas molecules have high energy, that's why they can vibrate and they can, you know, like jiggle about and everything. Solid, in a crystalline solid, the solid atoms, they don't have as much energy as compared to gas atoms, gas molecules, of course. High energy means high temperature, and at a higher temperature it's more symmetric. As the temperature is decreasing, as you are cooling down the system, you are lowering the temperature, you are getting like the symmetry is getting broken. Water vapor, water, ice, or gas, liquid, solid, however you want to think about it. But now here is one interesting question which you should ask, if you you might ask, is that, okay, fine. So gas, you are saying it has the maximum entropy. It's symmetric. Now if you try to think about it in terms of entropy, now does a gas has more entropy or solid? Of course the answer should be gas, because the gas molecules are free to move about anywhere, in any kind of way they like. So there are many more number of possible configurations, position configurations of the gas system of gas. Even energy configurations, more number, because gas molecules have more energy than solids. So it has more entropy than as compared to ice, or even a crystalline solid, because in a crystalline solid, the solid atoms are allowed to vibrate, but they are not like, they cannot move about as freely as a gas. So the number of allowed configurations of the system is less than gas. So the entropy is also less, right? So more entropy means we know it's more equilibrium, that's less energy. But here it's like, okay, a gas has more energy than solid. It also has more entropy than solid. How come? Gas has usually it exists at higher temperature than solid, so kind of it has more energy. But so it has more energy. At the same time, you're saying that it has more entropy as well. Doesn't that sound a bit counterintuitive? So it's like see, there is an answer to this question, and I want you to think about it. I will not see. It's actually a bit I understand it actually is very counterintuitive. When I first stumbled across this question, I was like really it disturbed me a lot. Like I was kind of bewildered. But there is an answer to the question, and yeah, it's not true. Like there is no general rule of thumb what is said about temperature and symmetry. But yeah, you can see this behavior even in cosmology. I gave you a very simple example about ice, water, and everything, which are like you can see in front of you, right? Like everyday objects, day-to-day daily life objects. But the same thing you can see in cosmology, like when the universe began, or even in like not only cosmology. This is also part of high energy physics. It is assumed, according to the GUTs, grand unified theories, gravity, other than gravity, the other three forces, weak nuclear force, strong nuclear force, and the electromagnetic interaction, electromagnetic force, they were supposedly, unified together into a single force, like a super force, which is often called supersymmetric force. So since they were unified together, and that was at very high temperature, see, the universe began in a very hot, dense state called the Big Bang. So very high energy, high temperature, and the universe was very like just a point at that point of time. As the universe is expanding, its volume is increasing and it's cooling down. Of course, the temperature of the universe is decreasing over time. It's cooling down, right? It's cooling down, and so it's cooling down, and symmetry is broken in the process. This is what we call spontaneous symmetry breaking. Spontaneous symmetry breaking is a very interesting concept in high energy physics, standard model, particle physics, everything. But it's very interesting to know that this concept is actually originated from condensed matter physics when we were studying magnetism and all, ferromagnetism and all. Just mention this because just to impress upon you how interconnected all the branches of physics are. For that matter, all the branches of science are. Because today in today's world, the problems which we are facing, like theoretical riddles like quantum gravity that seem impossible to solve, or practical challenges like climate change which seem insurmountable. So faced with these challenges, science and research should be interdisciplinary in today's world. That's very important. It's not like I am doing theoretical physics, you are doing condensed matter physics, he or she is doing biological physics. It's all interconnected. I think you're using the same principles, you're using the same physics. Science is science. It's very, actually I didn't know this. I recently came to know about this and I was like blown away. Oh my god. I've been thinking about spontaneous symmetry breaking for all this time, but I never knew that it actually came from condensed matter physics. But we're using this in theoretical high energy physics. So anyway, that was just for your the point is, so now all the three forces were unified back in the early universe. So at that point of time, entropy was of course less, because of course I'm not sure if we can say like this, but I think entropy was less because the entropy is increasing with time. That is an established fact according to the second law of thermodynamics. So must be entropy was less at that point of time, comparatively low entropy, and symmetry was also high. I mean, of course, the three forces are unified and it's asymmetric because temperature was also high. If you think about it, that was the gas phase. If you think about it like this, from what we discussed, if you try to draw a parallel, that was the gas phase. It was high energy, symmetry was very high there. Now, as the symmetry is broken, we have got three different forces: electromagnetic, weak nuclear, strong nuclear. Just like, see, in the gas, the symmetry was not broken. That's why we could not distinguish between all the sides. But in case of solid, we can distinguish if we don't shift by the allowed amounts, discrete translational symmetry. It's the same thing there. If you don't see, at that point of time, we could not have distinguished between the three forces. That is what we mean by symmetric force. Now we can distinguish between electromagnetic interactions, weak and strong nuclear forces. And this has happened because of spontaneous symmetry breaking. Very interesting, very important concept. So, but again, you see, entropy is increasing. This entropy part you do not try to relate, because in case of gas seems to be at a higher entropy than solid. But here the entropy increases from that super force to this today. That's a different thing. So we usually what we do, like very relevant and interesting problem in cosmology and astroparticle. I mean, you can say cosmology and astrophysics and particle physics kind of an intersection. Dark matter. So the dark matter density, it is usually assumed that there is a particle bath in the early universe, and there is a dark matter consideration also. So point is, we're trying to understand baryogenesis. Why is there more matter than antimatter when they should have formed in equal amounts and annihilated each other? Then you have the Shakarov conditions. There are three conditions which must be satisfied for there to be an asymmetry in baryon number. I mean, more matter than antimatter, or the other way around, right? So then there are a lot of other questions, like why is the dark matter density the way it is, the observed density and all. So to do this, what you can do is you have to study phase transitions. When a symmetry is breaking, for instance, electromagnetic, when we had the electroweak phase transition, that is the point of time when the strong force is already separated from the symmetric force, but the electromagnetic and the weak forces, they were still together. Electroweak phase. Now that a further symmetry breaking took place and the electromagnetic force and the weak nuclear force separated. And that we can model it using a first order phase transition. Phase transitions are very interesting concepts in thermodynamics and even in statistical physics, everywhere in physics basically, not just that. So why does this happen? Because of Higgs mechanism. This is where the Higgs comes in. We usually say that the Higgs boson or the Higgs field is responsible for generating the masses of particles. Now it's not as simple as that. That is just said. That's just a very layman, a very naive way to put it. But actually what happens is that in quantum field theory, we have a field associated with every particle, like every fermions are the particles that make up the matter, as well as every boson. Bosons are the particles that, like for instance, that carry the force, that mediate the force. Like for instance, two electrons repel each other because they're both negatively charged. Actually what happens is that two electrons, they exchange a photon. Photon is the quantum of light, and it's a massless particle. Photon is actually a boson. But electrons make up the matter. Electrons form a part of the atom. They're the fermions. So what happens is that when two electrons interact, they can interact in many possible ways. What they can do? One, suppose in quantum mechanics there is something called the uncertainty principle, which says that the uncertainty in energy and the uncertainty in time, the product must be greater than a constant. So that means if I borrow some energy from you, I have to return it to you. But the greater the amount of energy I borrow, the sooner I have to return it. And if I borrow a very less amount of energy, I can return it sometime after some time. You can think about it like this. So suppose there is an electron A and in the vicinity there is an electron B. Now suppose a photon decides to borrow some energy from electron A and materialize. Like there was no photon. Some energy of electron A manifests itself as a photon. It can happen in quantum mechanics. Vacuum fluctuations are also case, like virtual pair production, photons, all these things can happen. So now a photon borrows some energy from electron A and it comes into existence. Let's put it that way. Of course, the photon has to return the energy to electron A, right? It is bound to. But suppose there is an electron B in the vicinity and the electron B captures the photon before it can return the energy. So since the electron B captures the photon is a form of energy. So the electron B will get some extra energy and it will move away from electron A. So what I see is that electron B and electron A, they move away, they repel. But what actually happens is they exchange a photon, and the photon is the boson for the electromagnetic interaction, right? Now, two electrons can interact in many possible ways. Like they can exchange a photon, which I described. It can also happen like an electron A emits a photon, then it again absorbs a photon. Like there are many possibilities. Electron A emits a photon, the photon breaks into two more electrons, pair production. I mean, the photon breaks into one electron and a positron. Positron is a anti-electron, basically positively charged electron. Many things can happen, but if you sum over all the paths, it's called like if you take the contribution of all the possibilities, you see that in most of the cases, electrons or the like charges will repel each other, and that's why it's a rule that like charges repel. That's a fundamental rule of electromagnetic interaction. So yeah, anyway, this is the story of bosons and fermions. Now I was talking about the Higgs interaction, Higgs boson or the Higgs field. So all the particles, be it an electron, be it a quark, be it a photon, they have a field, quantum field associated with it. Now what do I mean by field is that just like a field means a mathematical imaginary like field of a particle, like it has some value at every point in space and time, and a particle of that corresponding field, like if I'm talking about the Higgs field, then the corresponding particle will be the Higgs particle or the Higgs boson. So a particle is just a vibration in the field, right? The field can vibrate at some particular frequencies, the allowed frequencies, and those vibrations manifest as particles. This is the basic picture of quantum field theory. The mathematics is very advanced, even I don't know all of it, but yeah, you understand, right? So now the point I want to discuss with you is, so yeah, actually what happens in Higgs is that when the Higgs field couples with, suppose we still have electroweak force, like electromagnetic and weak forces are still together, still unified, they have still, symmetry is not yet broken. Now, as the Higgs field will couple with this, first of all the weak nuclear force will interact with the Higgs field and it will take some mass, because for the weak force, the bosons, the mediators, they are the W boson and the Z boson, so they have mass, W plus, W minus, Z0. Z boson is neutral, it does not have any charge, but it has some mass, and the W bosons also have some mass, and they get this mass due to coupling with the Higgs field. By what I mean by coupling or interacting, it's not like the Higgs has a field and these particles also have the field of their own. So when these two fields interact, suppose you have a sheet and you have two sheets and they're interacting, so they will affect the frequency. Like the Higgs field will add some frequency, you can think of it like this, will add some frequency to the particle field, and more frequency means the particles will get some mass, because frequency means it's vibrating, the field is vibrating and it's giving rise to a massive particle, right? But since the weak force has already interacted with the Higgs, coupled with the Higgs field and separated, so what is left is the electromagnetic force. But now the Higgs field has no more energy to interact with the electromagnetic force. And that's the reason the electromagnetic force, the boson for the electromagnetic force, the mediator, that is the photon has no mass. Because the Higgs field has already coupled with the weak force and there is nothing left for the photon. That's why it has no mass. So you can think about it like this. The Higgs mechanism doesn't, one more important point, like the Higgs field generates the mass of the particle. So what's your mass? Let's say your mass is 40 kg, 50 kg, 60 kilograms, 70 kilograms, whatever. So do you think all that mass comes from the Higgs field? Of course not. You are made up of atoms, An atom is made up of some electrons which have negligible mass, and the main mass is considered in the nucleus, which occupies very little space in the atom, right? Inside the nucleus there are protons and neutrons. So a Higgs field will directly not give mass to protons and neutrons, because protons and neutrons are not elementary particles. They are further made up of quarks, up quarks and down quarks. Quarks, electrons, the electron class, electron, muon, tau are the neutrinos. They are the lepton, and there are 6 types of quarks. They are the quarks. So these quarks and leptons are the fundamental elementary particles, elementary fermions, and then we have the bosons. So these quarks, these elementary particles, they will directly couple with the Higgs field and get some mass of their own. Not the protons, neutrons or atoms, not the composite particles. But do you know that in a nucleus, if you suppose we have a nucleus of 2 protons and 2 neutrons, so we know that the mass of a proton, we know the mass of a neutron. So it's not like if we just sum the mass of 2 protons and the mass of 2 neutrons, we will get the mass of the nucleus. No, there is something called binding energy in nuclear physics, or even not nucleus. Suppose a proton. Let's go even deeper. A proton is made up of 2 up quarks and 1 down quark. So if you sum the mass of 2 up and 1 down quark, you will get very less percentage, I guess 1% or something of the mass of the proton. So where is the remaining 99% of the proton's mass coming from? That is because of the gluon, or the strong nuclear interaction. The gluon is kind of a mediator for the strong nuclear interaction. Or just to put it in simple terms, gluons and all, you leave this for the time being. To put it in simple terms, what's happening actually is that proton is very tiny particle. So these 2 up quark and down quark, they are confined within a very small space, right? So apart from their intrinsic mass that they get from the Higgs field, the mass that the up and down quarks get from the Higgs field, the gluons and the strong interaction is responsible for binding them together within that very short amount of space. And to confine those particles together, you actually have to have a huge amount of energy. And this energy is manifesting itself as the remaining mass. Most of the mass, in fact. So similarly, the majority of your mass does not come from the Higgs field. It comes from the energy. Energy means, this is again the basic concept was from Einstein's special relativity. E equals mc square. Energy can be converted to mass and vice versa. They are like equivalent. Very important. Okay, so, and you see the idea of Higgs boson is also the last thing I want to discuss before I end the video. It's already 27 minutes, and yeah, just wanted to discuss some interesting physics in this video. Nothing like particular. Okay, is that if you think about it, this Higgs field concept, it was entirely based on mathematics. When Peter Higgs made this prediction or made this proposal that there should be some particle called the Higgs boson, Higgs field, back in the 1950s, I guess, it was just an outlandish, and even some people say it's just a science fiction type idea. It cannot be true. Nobody has observed a particle. Why? Actually, Higgs assumed that initially, like in the very early universe, no particle had mass. So in that sense, why did he assume this? Because this made your calculations a lot simpler. This means all the particles were symmetric. Symmetric means if no particle had mass, you cannot distinguish them. So they're symmetric in that sense. But see how strange the claim sounds. Back in 1950s, someone is saying that all the particles did not have mass initially. I mean, are you crazy? We know a proton has this amount of mass, electron has this amount of, how come? Higgs said that the particles, with the evolution of the universe, the particles coupled with something called the Higgs field and got some mass. It was his idea, and it was like, and all this mathematics, the description of Higgs field, everything, it was based entirely on mathematics. There was no experimental reason, or there was no observation, no evidence no slightest reason to believe that something like this might exist. But see, based on the prediction, Peter Higgs's prediction, we actually found the Higgs field in 2014, I think, or 2012, I think, in the Large Hadron Collider, CERN, Switzerland. And when I say we found the Higgs field, of course, somebody didn't catch the particle and show that, see, this is the Higgs boson. When we're looking at what happens in these detectors and all these particle physics laboratories is that you collide two particles at very high velocities, and then very high velocities, near light velocities, and then due to the collision, the subatomic particles, the particle, suppose you collide two protons, and the quarks will come out, because the protons are made of quarks. So basically, if you collide two cars, all the internal parts of the cars will come flying out. If you think about it like this, very like kind of dangerous analogy maybe, but yeah, that's the point. So if it collide two particles, and then the internal particles will come out. Of course, you cannot see them. These are very like subatomic particles. But based on all this, there are many ways to detect gas chambers, scintillation detectors, many ways. So based on that, you can detect like which path the particles took and their energy and everything. Based on that, you can plot graphs and you can analyze. So it was like, for instance, neutrinos. Neutrinos were discovered, were predicted by Wolfgang Pauli because of, based on the beta decay, the conservation of energy and angular momentum, and even momentum was violated in beta decay. Because in beta decay, what happened was that it was observed that the particles, the products and reactants, they went like this, and that there was some resultant momentum. Although the initial momentum was zero, the final momentum was not cancelling out. That means there must be some other particle which moved in the opposite direction to cancel the momentum. But such particles were not observed in the gas chamber. That means the particle cannot have any charge. It cannot have any mass also. So then Pauli said maybe there is a particle which is chargeless as well as massless. It's a kind of an elusive ghost particle, but it has some energy, and that was a neutrino, and even the neutrino was observed. Many examples when such predictions were actually verified experimentally much later, like Dirac's prediction of antimatter based on Dirac's equation and all this, Feynman-Stueckelberg interpretation. Dirac predicted is antimatter prediction. That was also a theoretical prediction. So anyway, what I was saying is that, so then it was predicted that for this particular interaction, we should have a peak. Peak means there is this, usually we plot the probability of the cross section. The energy I don't know, it's GeV order or something, giga electron volts. In these particle accelerators, we use very high order of energy. We work with very high order of energies, right? So this is GeV order energy, and then we have this kind of spectrum here, and I think this is the energy, and here we have a probability of something, and we get a peak at some particular energy. So we can get a prediction from theory, like we should get the Higgs boson, the energy of the Higgs boson, or the mass of the Higgs boson. Energy and mass are interchangeable, right? So the mass should be here. So if we get a peak at this value, that means that is the Higgs boson. Peak means what? We have observed a particle, we have not observed with our eyes, but if we get a plot like that after from doing the experiments, that means that is how it was verified that the Higgs boson was discovered experimentally at the CERN facility, LHC, Large Hadron Collider. Because at that particular mass which we expect, we get a peak. That means a high probability of a particle existing in this reaction. That is what we expected, and we get that. So that means that we have every reason to believe that it was the Higgs boson that carried away that energy. Otherwise, everything would be violated, right? So yeah, this is the way physics progresses. We just make new predictions to fit observations, and then we verify those predictions using new experiments and new observations. Again, now this is the way physics used to progress. Nowadays, the theoretical physics scenario is very like saturated and kind of stagnant in the field of fundamental physics, theoretical physics. Of course, after the Standard Model is actually a very successful theory. Despite its arbitrariness and free parameters, it's actually a very successful theory. In some sense, you could say it's even more successful than GR, General Theory of Relativity. GR is more beautiful mathematically, more rigid, of course, more mathematically elegant. But which is a more successful theory between General Relativity and Standard Model? Probably Standard Model. But of course, yeah, it still remains the fact that Standard Model was more or less completed back in the many decades ago, and there has been no significant breakthrough. So again, I have discussed these points in some other videos, and maybe we will discuss some more in future videos. For today, I think that's enough for today, guys. I hope you found the video interesting, and yeah, see you soon. Thank you.